All right, welcome everyone to Flyte Community Sync. It's the first meeting in the year, and for those of you who are new to this meeting, this is something we do typically once per month. It's a space open for the community to share all the cool stuff they're doing with Flyte, and also come here to ask questions or like today to get updates on what's new in the project. I'm David Espejo. I'm part of the community, and also I'm with Union AI. And with me today is Eduardo, Niels, and Yi, who are all core Flyte maintainers. And they will be sharing some of the uh, highlight new features in the most recent major Flyte release, 1.14. If you want to dive into previous presentations, you can find all of them under the YouTube Flyte YouTube channel. There is a playlist. I think it's called User Stories or Success Stories. I will drop the link later on, and you can watch all the previous presentation. It's a treasure trove of learning of how people use Flyte in the wild. Cool. So with that, let's get started. We can go with the agenda. Yeah, Niels, please. Thank you. Yeah. So we'll move the intros at the beginning of each presentation. We'll cover from notebooks integration up to the preview on what's coming in the 1.15 release. Feel free to drop your questions in the chat. If you're watching on LinkedIn or YouTube, you can drop your questions there in the chat. We'll try to cover them at the end of each presentation, or if otherwise at the end of the session itself. Right? Okay, so with that, let's get started. So probably over to you, Niels, to cover the notebooks integration.
Okay, awesome. Thanks, David. Yeah, just to do a little quick intro, I guess Yi and Eduardo can also introduce themselves real quick when they get to their sections. I'm Niels Bentielen. I'm in the ML team at Union, but also one of the maintainers of Flyte. As you see in the agenda in front of us, we're going to start off with notebooks, then go into offloaded literals, data class and Pydantic support, a little preview of eager workflows, and then give you a little teaser of the Optuna plugin that actually leverages eager, and finally questions and answers. So real quick, as I mentioned, maybe in a kind of a LinkedIn post that I posted about this, love them or hate them, Jupyter Notebooks are here to stay in terms of a IDE that data scientists and ML practitioners use day to day for development and debugging. Before, Flyte didn't quite support this. There was kind of a paper mill integration where a notebook would be a node in your DAG, in your workflow, right? So you'd have to do all this stuff around the inputs of your notebook and then the outputs of that notebook as a node in your DAG. This is different. So what I'm showing here is the ability to actually define tasks in a notebook cell. As you can see here, we're also defining an image spec here that defines the Docker, basically the container requirements, as well as being able to actually run those tasks and workflows that you define in those cells in another cell, right? And so the result of this is execution that just basically runs the task that you defined on a Flyte cluster. This is super powerful because you may need some extra compute to do one thing that you want to do while you're, doing analysis or quick iteration on your notebook. Say I need a GPU or many more CPUs that are available in my laptop. I'll be able to actually define a single task that I can then run and grab the results in the notebook environment itself. So I'll show you that in a second, but at a very high level, I want to show you this quick diagram of the top here, which is how Flyte fast registration works today. All right, so you have your project and your workflow definitions and task definitions here. When we fast register, we zip them all up into a tarball, and then that is sent over to the blob store, which is then run on the Flyte cluster. So it's on all unpacked, imported, and everything should work. So if you've been a Flyte user, this has been kind of probably one of your main ways that you quickly iterate on tasks and workflows. The bottom here is how the Jupyter Notebook integration that I'm showcasing here that comes with Flyte 114, which is you define workflows and tasks in your notebook cells. And we actually use Cloud Pickle to serialize or to store and pickle up all of the functions and tasks and workflows that you define in here. And then we load them back in the task pod that runs your task. And that's basically it. So I'm going to hop over into my IDE here. As you can see, I'm actually going to use serverless, Union Serverless, which is hosted Flyte. You can think of it as the UI. There's a few differences in the UI, but for all intents and purposes for this demo, it'll just be the way I run this Flyte tasks. So this code snippet might look familiar. I'm actually going to go ahead and run it. And instead of running this locally, this is just a little toy data frame that I'm going to play around with. I'm actually going to create a Union Remote object, which is analogous to Flyte Remote. And I will execute the getDF task. And since it takes no inputs, it's just an empty dictionary. And now this is running on serverless. As I said, the UI should be quite familiar to you if you're a Flyte user. Just some of the colors and theme looks a little different. And now this task is completed. And so just imagine this is a create dataset task that is a little bit heavier in compute. And now I'm going to pull the output of that execution back down into my local notebook. And here it is. Here's the data frame. And to prove to you that I'm not lying, I can define this local function here that operates on this data frame that I just grabbed from the Flyte cluster. So this is a toy group by sum operation, just to show you that I'm actually operating on this data frame. Now, when you're iterating on the small pieces that you're eventually probably going to export into like a Python module, and you're going to productionize it, so on and so forth. But I just want to show you how this does not break the Jupyter development experience here by now training a model on the data we just created. So here I've defined a train model task and a very kind of dumb train model workflow. All it does is just wraps the train model task. In reality, I would actually do something like this, so I would actually use the task I defined before, but just for demo purposes, I'm going to run this, and it just trains a logistic regression model to predict whether a student passed the test based on their age. A very poorly formulated model, but again, this is just a demo. So I'm going to show you that I'm actually going to pass the data frame that's in memory right now in this notebook. I'm going to pass it into the training workflow. I mean, really, I could just pass it into the train model task, but let me just pass it into the workflow. And we're actually going to use the serverless build service. This is actually, I didn't intend to demo this, but just a little quick shout out to serverless having its own little build service here. So you can don't actually have to build the container locally. So this will actually add a little bit of runtime to my demo. So let's see what we can do here. Okay, so the image is building, and now it's the build is completed, and the execution is available on this URL. Again, this is running on serverless, training a model, and just gonna pull the execution until it's done. While we're waiting here, just a quick difference here between Union Remote and Flyte Remote that is probably worth mentioning. So with Flyte Remote, to enable Jupyter mode, Jupyter execution, you actually have to enable this flag. Interactive mode enabled equals true. This is actually just an opt-in flag. We'll probably remove this at some point. I don't know if others will comment on this, but yeah, we'll probably take this out at some point so that it's just opt-in by default. But for now, when you define your remote object, this is how you would do it with Flyte Remote. Okay, so now the model's done training, and I'm printing this model out here in the notebook itself. And just to wrap up the demo, I'm just creating a toy prediction data set of just ages of fictional people. I'm calling the predict proba method of the model, the sklearn model, and I'm just plotting out the probabilities here using pandas. So there you have it. This is essentially what I've shown you is you can define tasks in Jupyter cells and workflows as well. And then you can use the Flyte Remote object to execute them on your Flyte cluster. And you can, grab outputs from executions, pass those outputs down to downstream tasks and workflows as you're iterating on them. And cool. So next, I will hand it off to Eduardo, I believe. Eduardo, I guess you may want to share your own screen so you can control the progress of this.
Sure. Yeah, in the meantime, I don't see any new questions so far, but regarding the integration, I like the way this kind of, we are not, with this integration, we are not solving some of the core issues with notebooks, like, for example, it doesn't enforce order of execution or doesn't enforce building modular code or stuff, but really getting access to kind of a state machine where you can reproduce results and grab the outputs and move data between cells in this case. I think it's a major step towards making it reproducible. So
yeah,
so
absolutely.
I was wondering, and for the audience benefit, what are some limitations of this integration right now?
So I should have thought about this beforehand, but actually maybe Eduardo Yi, if you can chime in. I think, you can do a lot with this, and a lot of the limitations have to do with Jupyter Notebook limitations around just, as you said, out of order execution. So all of the kind of the footgun things that happen in Jupyter Notebooks, you just have to be aware of when using it with Flyte. As far as I've tested it, you can import modules that you've defined outside of the notebook. That works really well. You can also import tasks and workflows you've defined outside of the module, like in Python scripts, and execute them in your Jupyter notebook. But yeah, what are you? I don't know if you have any other.
I think the main caveat is just any caveat around Cloud Pickle. So we definitely ran into issues when we accidentally used mismatched versions between the Jupyter environment and the backend running environment. So that's probably the main one to be aware of.
Oh, sorry. Yeah, I totally missed this in the demo, but the Flyte Remote class exposes a from-env method, and that aims to kind of address that limitation where it will automatically try to pick up the Python version that is being used in the Jupyter environment. It also has an argument around the packages you want to match that are installed in your Jupyter runtime, right? So with example, scikit-learn, they're serialized and deserialized with pickle. So if there's a big fat warning that is printed when you try to deserialize sklearn model where the versions are mismatched. So the from-env method tries to match or pins the versions to whatever the sklearn version is that it's installed in your Jupyter runtime. So that's one way we've tried to get around that particular limitation.
Right, that is great. Yeah, the other, and by the way, this integration is possible thanks to contributions from many people, and especially Michael A. So shout out if you're watching. And even Michael put a nice blog that I'm sharing here. And yeah, he mentioned that probably another way to also kind of work around this challenge is by using image spec, a way to have consistent dependencies throughout different dependency versions throughout different environments. Awesome. That's great. I don't see any other question. So
sorry, quick correction on that. The from-env is actually on image spec, not Flyte promote. I misspoke there.
Okay.
Yeah.
That is better. Thank you. Cool. All right. So yeah, thank you. Now over to you, Eduardo. I can add this here.
All right.
And feel free to introduce yourself.
Just quick check. You guys see my screen, right?
Yeah.
Great. Cool. Yeah. So I'm Eduardo. Excuse me. I'm the engineering manager of a team at Union called DevX, or Developer Experience. As you can imagine, we're really passionate about making the lives of people who use Flyte, especially the SDKs, really, really useful. So this was one of the features that people complained about, and we invested the time to finally make it a reality. It's offloaded literals. So before we talk about what this thing is, let's start with a simple example. And the way I like to read these simple examples is usually like starting from the workflow. So let's start from the bottom. We have a very simple workflow here. It takes a single integer as an input and produces some inputs. For the purposes of this demo, we really have just like a list of the length n that you passed in as an input, and we use one of the favorite Flyte constructs, a map task. So we're essentially mapping this function, this task calculate, over the input that was generated, and finally consuming that list that is produced by the map task. For this specific example, like imagine that calculate is this complicated computation that produces at the end of it a really long object. In this case, a string of the character X. I know Python uses Unicode characters, so this is not exactly a megabyte, but suppose this is like a megabyte long object. All right. If you try to run this with smaller values of n, things work fine. You're happy. Now you try to extend this to larger lists, and you're met with this enigmatic error. Like, why are we even talking about like these megabytes here? Like, why are we talking about like max downloads? What is this? So let's dive right in. First, a little refresher on how Flyte handles data. From the 10,000 foot view, there's really like two kinds of data that Flyte worries about. There's metadata, and there's like actual like raw data. Making an analogy with regular local computers, you can think of metadata as like these small values that are threaded in as you make functional calls. And here's where the limit of like the 10 megabyte limit comes up. Metadata is available to all Flyte components. So let's talk about a subset of the components that are involved of like how we pipe data in and outside tasks. So here, in the middle, we have your user code, a task that has access to inputs, input metadata, and also like input like raw data. These are all stored in some blob store somewhere. And the interesting detail here is that all these objects, they end up being described as protobuf messages. So if we go and run the day in the life of a piece of data in a task execution, um, Propeller is the actual engine that prepares the metadata to be passed into tasks, and that's how we also like pipe and make sure that data that's emitted by tasks are also available to tasks, that downstream tasks. So if we double click on what actually happens when data is about to be handled by a single task, you can think of it as um, you have inside your Flyte task when you do and when you use the decorator add task, what actually happens is FlightKit has a little bit of code that transforms these protobuf messages into native Python objects. Excuse me. And it is around here that we're gonna do some magic to ensure that these cryptic errors that we're seeing can be resolved by the runtime without really any user input. But again, I just double clicked on what a FlightKit task, how it looks like. You get both input metadata and like raw data being piped into type transformers. The FlightKit SDK transforms these objects into actual Python native objects that get executed by your user code. Your user code produces, Python results, Python objects that get translated back into protobuf messages. If you go now and read the protobuf docs, they have this section there that says, hey, protobufs are really not super well designed for large messages. They even give you this general rule of thumb, which is pretty impressive. But they say, hey, if you have a message that's crossing the megabyte limit, you should really consider alternative strategies. One could read this and like really think like, why is the gRPC or the protobuf team at Google really saying this kind of thing? If you think about how messages are both like produced and handled by servers, like if you can make sure that messages are all like well limited, they're small, this can prevent resource usage, right? Like imagine you have a server that's handling like thousands of connections. If they need to keep these big messages in memory, these servers will suffer. Network bandwidth is also a concern. Well, since you're handling connections, like you need to be spending some processing power to ensure that the connection is actually handled, the messages are built. And by having these limited messages, gRPC really reduces the risk of out-of-memory errors. If you really have like these large messages, the gRPC documentation advises you to use different strategies, maybe enable streaming for your gRPC calls, or you can offload these large objects and you just like put a link to external storage or whatever you are storing these messages. Another consideration here for gRPC really leaning on this idea that the messages should be small is that this also prevents the kind of like denial of service attacks. Imagine the case you have a bunch of like thousands of connections. If for whatever reason one of your endpoints is doesn't have auth setup, or even if auth is enabled, like you might end up having downtime in your server just because you let a malicious agent create thousands of connections and consume all the resources in your server. Seems like gRPC by default doesn't really implement like quality of service or anything. I know that there's a way, but like the regular run-of-the-mill gRPC server doesn't let you do that. So we took the advice of offloading these big portions of a message, and we offload them by implementing the fundamental theory of software engineering. Here, fundamental is in quotes because really there's nothing mathematical about this. It's not predictive. It's really tongue-in-cheek. You can really solve any problem in CS by adding on the level of indirection. And that's what we did. If we go back to that small diagram that showed how data flows in and out of a task, the SDK now makes sure that you can read these offloaded data pointers, so to speak. And every time that you have some user code that produces these gigantic monsters, we make sure that they are now offloaded to the blob store. So it's kind of like the best kind of feature. Like the user code is completely oblivious to the fact that we are doing this offloading from and to the blob store. There's no like opt-in from the user coder's perspective that to use this feature, really. So now let's run the motivating demo. So just to show what we have, hopefully we're just running this. Again, it's very simple, and I even called it the innocent.py example. But now we're going to run this with n being 10, which would cross that limit that we saw in the beginning of the presentation. If we now go and take a look at one of these executions, now consume list, which was a thing that was failing before, now it succeeds. That I'm not lying, this thing returns, like go back to the code, consume list really just returns the length of that list. So again, it's a very simple example to show that I didn't have to change anything in my code to make this work for small inputs and now like larger inputs. And now let's talk a little bit about the limitations, right? Like now the Flyte users are very familiar with this sidebar that shows on the right, where you can inspect the state of the executions, the attempts, the inputs and outputs, and like the task definition. Now, if you go take a look at like how inputs look like now XS was supposed to be, let's go back to the code. XS was supposed to be a list of strings, right? Produced by the map task. But if we go to Flyte, the Flyte UI, the Flyte console UI, the inputs now show this thing like the name matches, but like this is not the object that you define. Like it's just saying I now offloaded this object to this location here, and you can even see that it mentions like metadata bucket. But this is one limitation that we have in the visualization of offloaded data. Even if when the task runs, FlyteKit is responsible for transforming like in and out of this format. We are shipping this feature. We find it very useful with this limitation. It's well known. We are deciding how to invest in this. And another limitation that we are also like we plan on fixing much sooner is this demo that Niels just had with Jupyter, which under the covers really is about Flyte Remote. You need extra configuration to be able to consume these offloaded objects from outside of the cluster. Again, from inside your executions, nothing changes. Like we offload the data and we load it in Flyte Kit 114 and up. But from the outside of the cluster, we still need some work. We're shipping this feature with these two limitations that we plan on addressing pretty soon. You could also ask like, how do we expose this to actual Flyte deployments? We decided to ship this as enabled by default in Flyte 114 across all deployments. So now we offload the data if the objects that you are returning are larger than 10 megabytes. We have a max size of 1 gigabyte. Both are configurable. If your use case requires, you passing these larger objects, feel free. And does anyone have any questions about this?
Well, I don't see any from the audience yet, but I had one. I mean,
Okay.
I enjoy how this particular enhancement reduces the need for kind of setting arbitrary limits in configuration for the max size of the gRPC data. And wondering, again, for the benefit of the audience, what if I need to pass objects larger than 1 gig? Yeah, well, it will fail, like it will produce an error. But in general, what Flyte offers in terms of abstractions to move really large data?
Yeah, so I guess now to answer this question, like we should go back to like the kinds of data, like like Flyte users, they are familiar with some of the abstractions that Flyte provides. Regard to your question, David, users can use, like, for example, like Flyte files to produce these gigantic objects, right? Those are not considered like metadata. They are already offloaded to the blob store. So users who really need to think about this, they need to get into the bowels of like how type transformers work and like what is the kind of actual protobuf message that those produce. But yeah, I would say Flyte Kit has a few abstractions that let you not worry about this distinction between what gets offloaded versus not. And for the cases where you need like these really large objects, now you have a few options. You can either write them using like Flyte files, or now starting with Flyte 114, you can just pass them around as you used to. But yeah, the TLDR is that if you really need to worry about like passing these large large objects from your tasks, you should get familiar with how type transformers are defined and what's the kind of data that they produce. I don't know if E or Niels want to jump in here, but that's the overall design. Like we have some abstractions to help you pass these large objects around. Like good examples, like how data frames are produced. Like we don't inline the data in these proto messages already today. Like they all get the actual like raw data of data frames. They get shipped to blob store, and we just pass like these little pointers or addresses really between tasks. But there's no hard and fast rule. Like you really need to understand like what is the kind of data they are dealing with and how the type transformer is defined.
Thank you. I think there's a related question from the audience. What are some use cases you might expect for uploaded literals being used out of cluster?
Yeah, I think the idea here is like this flexibility that Flyte Remote and Jupyter in general gives you, right? Like imagine you have this need to just extract some data that was produced by a Flyte execution outside of the cluster. Like you're just loading, I don't know, you're writing like a new inference service, and you just want to point to a specific model that was produced by a Flyte execution. Like you want to extract that, but still like be within the bounds of the abstractions that Flyte gives you. I think remote opens up a huge set of really capabilities to Flyte. And the fact that we don't have support for offloaded literals yet in remote is a limitation. So should address it.
Got it. Thank you. We hope that really answered your questions. But otherwise, cool. Any other comment around offloaded literals? If not, thank you, Eduardo. And yeah, we can move to the next presentations with Yi.
Thank you. Let me share my screen. I'm gonna hop on over here. So, hey everyone, my name is Yi. I work under Eduardo on the DevX side, mostly working around the Python SDK Flyte kit. One of the features, I guess, that users often tell us that they appreciate about Flyte and Flyte kit is the ability to hop out of the typed paradigm and just pass arbitrary dictionaries around, or typed but arbitrary structs like data classes and Pydantic models. That's been supported. This statement's kind of not entirely true. There has been support for Pydantic, but not out of the box. You have to install a plugin. But one of the issues has been around the typing. You may have, if you've tried to pass an untyped dictionary hyperparameters around to scikit-learn, for instance, you will have come across as a weird error where the integer that you give it gets translated into a float, and then it gets confused. And we've also heard complaints around the size of serialized data classes and models, Pydantic models. The ability to do offloading notwithstanding, if you're passing around many thousands, if you don't have to offload, which again wasn't available until recently, if you don't have to offload the serialized form of your data classes, it is better. So when you get up to the thousands and tens of thousands, the size of what Flyte was using for transport was becoming apparent to some users. So in 1.14, we've changed the transport mechanism to use message pack. So this is maybe not compressed, but it is efficient by default. I believe is their marketing term. It resolves the confusion between floats and ints, and we've also moved Pydantic support into FlyteKit core. So the transformers and everything just get loaded if you have Pydantic installed. And you can come up with some pretty, we've tested it with some pretty complicated models, nested models, and the Flyte primitive types that FlyteKit ships with, like directories and files. Just a note, I think we are renaming these types, aliasing them to file and directory in upcoming releases, not the next one. Attribute access will also continue to work. So you can pass in, I think right here is probably more relevant. You can pass in the access attributes of a parent model and pass them as inputs to tasks underneath. There are some edge cases around this, so let us know if you run into them. If they don't yet work, this will be fixed in a future release. They don't yet work for, I believe, non-primitive types. And yeah, that's it for the message pack discussion. I also wanted to mention that in the next release, so not 1.14 but 1.15, we are going to make some breaking changes to the eager syntax. So this is it's been in experimental mode for a while. It remains in experimental mode, but we are basically updating the syntax a little bit. So as a background primer, if you haven't worked with them before, what are they? You'll hear us refer to them as eager workflows. Technically, they are still defined as tasks, so they are actually Flyte tasks. They are tasks that orchestrate other Flyte entities. And each entity is then launched as a separate execution on the platform that your eager task is configured with, and it must be configured with a backend, like remote API endpoint. As those executions run, those outputs are materialized as Python native values in the container that is running the eager task. So then you can use kind of like the Jupyter Notebook demo, but you can use the Flyte platform integrated with the expressiveness of Python. So like, just as an example, think if statements instead of conditional. The reason this remains in experimental is because it breaks some of the assumptions that Flyte was built with. So like, for instance, it becomes very, very easy to DOS your own Flyte backend, because you launch a out of control eager task that just spawns millions of executions against your API server. So it remains experimental, mainly because we want to think about ways to protect against things like that. How exactly is the syntax changing? Basically, previously we had some code in place that allowed the syntax to look a little strange and not quite like what you might expect. Basically, tasks implemented their own await function. In the new model, we were doing a couple things. One, introducing the concept of an async task explicitly, removing the ability to await a non-async task. And you must, like in regular Python async programming, you must await async tasks. And the eager task itself remains async. And I think here, if you used it, you'll probably have configured this section here with a complicated series of configuration. That has been made easier. It will automatically detect the correct settings as defined as environment variables and create a remote object for you. And with that in mind, there is a quick little demo that I'm going to hand back over to Niels to do in this vein. Wait, Niels?
Let me see. I'm going to share screen. Yeah.
I was gonna let Niels share his screen. I think he has.
Yep. So you should be able to see this demo screen right now. Actually, I'm going to jump ahead and demo a more realistic example that is a hyperparameter optimization example that one of our very own Grantham has built out with Eager. So this is a little bit more complicated, but hopefully still simple and legible than the examples that he was showing in the slides. But this is an example that kicks off a bunch of optimization jobs, a bunch of objective tasks here, based on a very simple mathematical function. But this, you could think of this as an ML training run that produces some kind of performance metric that you want to optimize for. And you would use something like Optuna as a hyperparameter training framework to do this job. But I want to show you how to actually do this on Flyte with Eager. So I'll go back and kind of show you sort of more theoretically how hyperparameter optimization has worked in the past on Flyte, and hopefully we'll be able to circle back and connect the dots. But here we're defining a task, as I said earlier, that's that evaluates some kind of objective that isn't differentiable. So you kind of have to do some kind of random search or Bayesian optimization or something like this. And we define a eager workflow here called train. And you can kind of think of this, if you're kind of deep in the weeds of Flyte, you can think of this as a task, really, that has access to a Flyte remote object that can kind of kick off arbitrary subtasks and sub-workflows. In this case, we're defining a optimizer object here. And I won't go too deep under the hood here, but I do want to just emphasize that this optimizer object is defined as a data class that exposes some async methods. And I want you to think about just native Python and async Python here. There's nothing here that is special and Flyte specific. You could define this, basically it defines a call method that uses async io.semaphore, and it spawns a bunch of different subtasks basically underneath here using this spawn method. And you can just think of this as I want to run 100 different hyperparameter settings with a concurrency of 10, for example. And this is just defined in native Python. So maybe a little bit more advanced, but still hopefully pretty legible here. And when we await the optimizer call method, which is right here, basically it will spawn those 10 concurrent subtasks with a total of 100 different runs, and it'll visualize a bunch of different things about this experiment run and return the best value. So we're not going to wait for the entire thing, but here I'm just going to kick off one such training run, concurrency of 3 with a number of trials of 6. And I'm just going to use one of our internal demo tenants here on Union. As you can see, this is just a task, right? But it has now spawned, it is going to spawn 3 concurrent subtasks that are running here. So we're not going to wait for this, but I am going to show you one that is completed. So this is one of those training tasks, the eager workflows that have completed. And I'll show you some of the limitations here, right? So since this is a Flyte task, we don't have yet a first-class way of showing the workflow, the eager workflow. The way we expose this is through Flyte decks. And you can see here in this timeline plot all the different subtasks through time that this eager workflow has spawned. So we can zoom in here. This is basically the start and end time of each of basically 1,000 trials here that's being visualized. This particular Optuna plugin, so quick shout out to Grantham who built this out. This kind of a preview. This will be released in Flyte 1.15. So this is a wrapper around Optuna that essentially implements hyperparameter optimization. And let me hop back onto my execution here. This shows the optimization plot. So lower is better. So objective value here, you can think of this as loss or something like that. And over the 1,000 trials, you can see how this training run has produced kind of this optimum value down here. And finally, this is kind of the way we expose all the subtasks that are spun up by eager workflows. So this is basically a list of all the sub nodes that this eager workflow has kicked off. If I can go, I could go here, and this is the task itself that has run the objective function. So a fairly involved example, but hopefully a real world example that you can relate to. So let me hop back onto the slides and kind of explain why this is so powerful. So for hyperparameter optimization, you basically have, from the very slow to kind of a parallelized setup. So you can have a sequential execution, which is super slow. So each of those 1,000 runs happen sequentially. With prior to eager workflows, you could use kind of batch dynamic. But if you've worked with dynamic, it's essentially a task that compiles a static workflow. So you kind of have to run each, in terms of specifying the concurrency, if you want to run, say, 100 different runs with a concurrency of 10, you'd have to run each set of 10 subtasks then sequentially as batches, right? Then finally, what you could do is use maybe a map task and use some kind of external storage that keeps track of the experiment history. But this also, requires external dependencies. You might use some other service like a Postgres database to do this with Optuna. But as I just showed you, with the Optuna plugin, Flyte plugin, and Eager, we can actually get the best of both worlds here. This is just a plot showing the Bayesian optimization run using this plugin that I showed you earlier in the UI. So there's a lot more you could do with Eager. Obviously, you can orchestrate arbitrary workflows. And this is a concrete example that gives you a lot of performance benefits just using pure Flyte and Python constructs. And that is it for all of the presentations. I think there's one back here about message pack. Yeah, David.
Yeah. Thank you. Yeah, there's a question from Gilbert that I think is related to a very fresh issue he's having. How message pack handles the union type?
Message pack should. I need to look into this a little bit more, but it should handle it fine. I saw the question that you're facing, so we'll be taking a look at it.
Got it. Thank you. And now another question. Why the eager tasks are not part of the colors execution back in the UI and instead launch a different execution like Flyte remote?
I think in it would I think users should be free to think about it as if they were. They are just not because of how the system was designed. The execution engine does not have an interface. And this is one of the assumptions that I was referring to. The execution engine does not have an interface to arbitrarily execute code. So that's certainly been something that we've discussed in the past, and we may or may not do in the future. But for now, the path for executing new executions routes back to the control plane.
Yeah, and just to emphasize here, to build on top of what he said, Flyte really was designed around this notion of a static workflow. Gets you a lot of benefits in production. Flyte is as popular as it is because of its reliability. And a lot of that has to do with the fact that you define this static at workflow kind of using our DSL. We compile it, we do the type checking, we do all that nice stuff. And that actually limits the scope of what a workflow can do. However, the trade-off is kind of ease of onboarding. So if you've onboarded with Flyte and used at workflow, and you've seen it as a decorator on a Python function, if you tried using other Python constructs like async and it just doesn't work, the reason is it isn't designed to work that way, right? So our motivation for using Eager or for building out Eager is to make the onboarding experience a lot more pleasant, to make it a lot more flexible, with the understanding that when you're productionizing things, you probably want to reach for the right tool, which is static workflows in this case. And so that said, the way we've implemented it through Flyte Remote is kind of the quickest way we can use the current building blocks we have available to provide this more flexible way of composing and orchestrating tasks. This will be a long-term project. This will be a long-term investment. So this is really just one of the first steps to make onboarding a lot more natural and easy, with the understanding that you'll have to learn a few more things, a few more constrained ways of programming your DAGs with static workflows when you want to productionize them. And then B, there may be some actual production workloads that require flexibility. And so this will be the tool that you would reach for in those cases.
Thank you. That is great. Yeah, I think it's a major investment because it points to at least two of the common adoption barriers for Flyte. One is the fact that the workflow construct is a DSL, not pure Python. And also there's usually this idea that the learning curve for dynamic is pretty steep, and in general parallelism. So yeah, I think this is a significant investment that probably will save a lot of time for Flyte users and union customers too.
And just to add to this, right? Like if you look at other orchestrators, a lot of them are DSLs, right? You write YAML files and you connect the dependencies in YAML, right? They do not expose anything about, like if you need Python, the node in that DAG just needs to do everything and you won't be able to observe anything that's happening inside. So we're kind of making this bet that Python's dynamism is desirable, and similar to sort of like the gradual typing philosophy in Python, where it is the Wild West, and then you can add these type hints, and then you need to adopt a kind of linter toolchain, type linter toolchain for this. Like it's not completely analogous, but that's sort of we're kind of doing the reverse of having a very strict DSL, and then we're loosening it over time. And this is based on demand. This is not just us feeling like doing this, because this is a lot of work.
I agree. All right. Any other comment? There are no sending questions from the audience, so I think this is very interesting. We finished on time, and this is the first time we do this in a while. So yeah, it was great. And yeah, but I was excited for the EUI now, for sure.
Yeah. We'll get to it.
Another major investment that is going to be great. Awesome. All right. With that, thank you all for joining. Hopefully we can make this work again in the future for another release or something like that. But again, if you have any other question, feel free to join Flyte Slack workspace and drop your questions there. We usually try to answer promptly. And yeah, thank you for watching.
Awesome. Thank you, everyone. Bye.
Thank you.